Okay, let's get started. So yeah, first of all, yeah, I got your feedback from the midterm evaluation. Yeah, I think it's very helpful, right? So let me think. I think one thing I may need to focus more and is that somebody asks me to cover more practical stuff, right? And how to apply, what we learned, how this can be, implemented or used in practice, right? This would be very hard. Okay, yeah, I will try. I was trying actually a little bit, right? Because so information theory is kind of like, we use theory for theory. So, and it can give you very high level instruction on the code design, right? For example, let's say, we use the craft inequality to give you the length of the previous code, right? And then how to construct the code, is your business, right? So theory normally cannot give you that. I mean, information theory. And the other thing is that, what we learned before is that, so from the entropy, right, sequential code can be better than block code, right? But how to design it, again, is your, you have to design it, right? And then very rarely, so the proof procedure can give you the design, idea. So one channel code that we have not covered that yet, but one is called error correction code or channel code for communication. It's called polar codes, right? So polar code is the beautiful code that theory proofs can give you the construction. Okay, normally you cannot get it, right? So unfortunately, so our class, is to give you theory and teach you how to use theory to prove another theory. It's pretty much applied math class, okay? But I think, it is very relevant nowadays, right? Maybe not before, but nowadays I think, how to, understanding theory and you can use theory to prove something mathematically. I think today is even more important than before, right? Because you see this AI wave, right? So every week there's a different model probably, right? And it is more and more powerful, right? And how to make sure what it does is correct or not, right? You need very broad and deep knowledge at the same time, right? Otherwise, if AI gives you something, there's no way to see whether it's right or not. Okay, so it means that you really need to understanding what is going on. In my opinion, so if you want to get a very high-paid job later, so I think this kind of job would be, so you need to know how to explain AI. For this kind of job, I think we need lots of such kind of people. If you have algorithm, it works very well, right? But normally, no people know why it works well. If you know why, then you are better than others, right? So this kind of person is what is really needed. I don't know. There's a very kind of hot, popular startup AI company in Silicon Valley. So it got lots of, funding. So I forgot the name exactly, but there are a lot of people from, the founding people. I mean, the founding people for that company are from OpenAI, from Cloud, from all this great company. But the goal of this company is to explain AI. I think that is extremely important, right? So information theory can help you on that, right? So this is one angle to understand how AI works, right? So now we're focusing on compression, right? And as we said, so in AI, this foundation model is somehow kind of a compression mechanism, right? So this can help you to understand the model somehow, okay? Yeah, just to be clear on that. So you may not see how we can use our theory to give you a practical code, okay? So there's a gap there, okay? But this gap is another class, right? So it's not this class, okay? For example, I think I don't know whether we have it here or not. Normally there's another class called error correction coding, right? So that's to teach you the coding algorithm. Okay, practical coding algorithm, but not for source coding, for channel coding. Okay, so I took this kind of class before. So when I was in Sweden, as I discussed with you, so I have one class on data compression to teach algorithm, and I have another class on error correction codes. Okay, but information theory is an independent one. Okay, but this is from the root, so just make it clear, right? But it doesn't stop you to think how to use this to design real code, right? So you can think in that way. So Okay, hopefully, but yeah, you give me a very good comment, so I will try to modify to see whether, okay, you are happy with that or not. All right, okay, let's see what we covered in our last lecture. So in our last lecture, we finished talking about optimality of Huffman codes, and then we talk about Shannon-Fano alias code. Okay, and for Huffman code, we say, so Huffman code is exactly optimal, okay, for any n. Okay, so this happens pretty rarely. Normally, if we see optimal code, it may be optimal asymptotically, right, when n goes to infinity. But Huffman code is optimal for any n. Okay, but this under some consideration, right? First of all, so it's a block code, and second, so we need to know the probability distribution. Okay, and that is very important. All right, and the proof is by induction, right? So we say if we have two symbols, it's pretty obvious that Huffman code is optimal, right? Because you cannot. Oh, another thing I forgot to say is that it is also zero error code, right? If it's not zero error, then Huffman code may not be optimal. Okay, so then if I have two symbols, we know one bit is optimal, right? Huffman, not one bit. I mean two symbols are optimal, right? 1, 0. Right, so obviously this is optimal. Why is it optimal? Because we need zero error code. Okay, otherwise it may not be optimal, right? And or we don't know that. Okay, and then we choose. Okay, so for two symbols, I mean obviously Huffman is optimal, and then then we say if we do an expansion on this two code, and if this m-1 is optimal, then m would be also optimal by expanding the code. Okay. And that's how we prove that by induction. Right, and then we move to the Shannon-Fano alias code. Okay, so basically the idea here is that we use a single digit in 0 and 1 to represent each source symbol. Okay, and then we just need to make sure. Okay, so yeah, we say it's a digit. So the reason we say it's a digit is that we need to truncate the digit to have a real code, right? But actually, the interval represents each source symbol, right? So what we need to do is that we need to make sure the interval will not overlap with each other, right? We just take the midpoint in the interval to be the digit that we want to encode, right? Now we need to make sure the interval is not overlapped with each other, right? And we prove that actually, it is true, right? If it is a prefix code, okay? And so basically, the SFE Shannon-Fano alias code is a prefix code, and the average code length is given by this formula. And of course, we have a lower bound, which is n times h of x, right? And you can see the performance of this code is even worse than Shannon code, right? Because we have a +2 here, the Shannon code we have a +1, right? So performance is worse than Shannon code, but the big advantage of this code is that so we don't need a code book, right? We can compute it online. Right, because for each code, for each source symbol with length n, right, we could compute the probability, right? And if we know the probability, right, and then we know, which digit we should encode, right? And the length of this is the ceiling of minus log p plus 1, right? And so this is how it works, right? You can compute it online. You don't need a code book, right? So it is a save of lots of storage, right? But for large n, computation of this code can be very hard, okay, can be impractical, right? You can see there's a problem for this code as well, right? To solve this problem, so we can introduce arithmetic code, right? And so you can read it offline, right? We don't discuss much of the arithmetic code, but the idea for arithmetic code is that we code the sequence sequentially. Okay, so basically code the first symbol, and then we have a range between 0 and 1, right? And then we within the new range, and we have a new symbol coming in, and then based on the probability, we encode another one. Then we have a new interval, and then we keep going, right? The interval will shrink smaller and smaller and smaller until the end. Okay, it basically means that for a whole book, right? If you want to encode it, it's just single digit. Oh, sorry, a single number. Okay, you can do the whole book, right? Okay, but another advantage of this kind of coding is that, as we said, for all the codes we have learned, right? Shannon codes, Huffman codes, Shannon-Fano alias code, for all of them, we do need to know the probability distribution. We do need to know PMF, which is a big constraint, right? But arithmetic code, we do not need it, What we do is that we estimate it offline, right? If we see there's a, let's say, okay, we assume, for example, we can assume a artificial beginning point as 0, right? If next symbol is 1, then we know the probability of 0 is half, probability of 1 is half, right? If we see another symbol 1, then the probability of 0 is 1/3, and probability of 1 is 2/3, and so on. We can update this probability, and eventually we're going to learn the probability distribution, and it will become optimal. Does that make sense somehow? Right? So the reason we don't cover arithmetic code is that the computation of that is extremely difficult. I mean, very complex. There are a lot of ceiling and the flooring we need to do, and so in my time we need to compute that by hand, but I don't think it worth it. So we need to spend, I think, at least like 90 minutes to cover the whole thing. So yeah, I didn't cover that last time, so I'll skip it this time. But you can, but the idea is it's very similar to SFE code. Okay, so you can check it offline to see whether you are interested or not. So this is a practical source coding scheme. We use that in practice. Okay, very good. And for today's lecture, we're going to cover a few topics. 23. So hopefully we can finish talking about source coding today, and then we can start a new chapter next class. Okay, the number 1 is mismatched Shannon codes. Okay, so here basically we want to see that, okay, when the probability is not exact, then how much do we lose, right? You may guess, right? So we kind of mentioned that before. Okay, and the second topic is that, so we're going to see the competitive competitive optimality of Shannon codes. Okay, so basically we're going to say that Shannon codes is pretty much optimal. Okay, so if we consider, the average performance. Okay, and then so we'll cover the universal compression of binary sequence. So this is a case where, let's say, if we have no idea on the PMF, what should we do? Okay, or what is the most obvious thing that we could do if we do not know the PMF, right? And if we do that, how much do we lose, right? It's not a lot, actually. Okay, and finally, so this is the last topic for our class. So it's called, so this is the last kind of coding that we'll cover. It's called lamp-positive. It's called LZ78 because it was introduced in 1978. Lamp-positive universal compression, right? So here, again, you don't need to know the PMF, and you can do pretty well, okay? And this is the sequential coding. So yeah, we didn't cover much about sequential coding yet. So arithmetic coding is a sequential coding, but we didn't cover that in detail. Okay, so let's see the number 1. So revisit of Shannon codes. So I have 2 topics here. So number 1, we're going to see when the distribution is now known. Yeah, not 2, just 1 topic. Okay, yeah, this what I see. Okay, yeah, there's some mistake here. So basically, for the mismatch Shannon code, why is yeah, I don't know. Yeah, let's do it this way. Okay, I think. Okay. Yeah, so basically what we're going to do is that we're going to cover mismatched Shannon code. Okay, So basically, it means that if we do not know the PMF exactly, instead of Px, we use Qx. And then we're going to see what do we lose. Okay? So can I take a guess? Right, let's say, so Px is a real PMF, but instead of Px, so what we can estimate is Qx, right? So if we use that for our encoding, let's say we use Shannon code, and how much do we lose? Yes?
Is it the divergence?
Exactly, right? So it's almost obvious, right? So we kind of mentioned that before. So the reason we define the KL divergence or relative entropy is to measure this, right? But at that time, we don't have exact code there, right? We just use minus log px, right? For that is, if that's the code length, and then if we use q, then what we lost is the KL divergence between p and q, right? This is what we said, right? But now, so we'll almost repeat the same thing, but now we use a real code length, which is Shannon code, right? We have a ceiling there. So it will make things a little bit different, but not a lot. Okay, let's see. So it's kind of a review, right? Let's see whether this makes sense to you or not. So basically, we'll let xn follow px, okay? And let qx be another PMF. Defined on xn. Okay, and then the average code length satisfy the follows, right? So we define the average code length again as this, not average code length, sorry. The code length is this, right? So this is how we do the Shannon code if we only know Q, right? Okay, and then what we can get is that the average code length 1 over ln, right? So we have a lower bound and an upper bound, okay? And the lower bound is given by h of x, and plus what we learned before, the KL divergence between px and the qx. Okay, and for the upper bound, it's almost the same. So, right, wait. So it's not a vector. So we do a normalization here. So it's singular. Okay, qx. And the upper bound is h of x, and then we have this. Qx and then plus 1 over n. Okay, and here we assume it is DMS for simplicity. Okay, there are in IID. Okay, so let's prove it. The proof is almost trivial here. So we just need to prove the upper bound, lower bound can be followed exactly like this. So basically, if we want to compute it, the average length, so we need to compute this guy. Right, so, and then we can have upper bound. So if a lower bound, we just, if we get rid of the ceiling, it will be a lower bound, and then the proof will follow, okay? So for the upper bound, we just need to add a 1, right? So this is upper bound, right? And then we can multiply this inside, log qx, and then add 1. Right, because px multiply this and sum over all the px, so the probability will become 1, right? Okay, so now we're almost there, but what we miss here is that we don't know, or this p log q, right? So we need to manipulate this a little bit to get entropy and relative entropy, right? The way that we do this is as follows. So basically, we're going to add this term, px log px, and then minus this term. Px. Okay, and then add 1 here. And we can see, so what we did here is that So here is just a entropy, right? And here is a negative entropy, right? And after doing this, so we could kind of combine the first two terms, right? So basically, let's combine the first two terms. So px log px over qx, and then add hx, add 1, right? And then the first part is nothing but the KL divergence. Wait, we have an n somewhere, right? So let's say here is n, and then it's a vector. Hopefully it is clear, right? And then because it is DMS, right? And then this equals to n times dp qx and px and qx add hx n and plus 1. Okay, and then we divide n on both sides, then we're good, right? So assume it's DMS here. Okay, so this is the upper bound, and similarly, we can show the lower bound. Similarly, the lower bound follows. Okay, you kind of did that before, but this is for a real code, right? For Shannon code. Okay, and now let's see the competitive optimality of Shannon code. Okay, so this basically tells you that, so if Shannon code is not as good as other code, then, how much worse, right? Or, compare, so what is the probability that the Shannon code will be worse than other codes? Something like that, right? So basically, we have another theorem here. So yeah, the condition of the pretty much theorem is the same as before. So here, just let's say this probability is even this length is the length of Shannon code, and L prime is the length of another code. Okay, so if we have this, then the probability that the Shannon code, let's say we have length n here, block length, is bigger than L prime xn plus c is less than 1 over 2c minus 1. Okay, so remember here is the probability of this, the length of Shannon code is bigger than the length of other code plus c, right? And you can see that when c becomes larger, and then this probability becomes smaller. Okay, so basically, in case Shannon code is worse than other codes, then what's the probability it is worse? It's longer than like C. Okay, you can see, when C increases, then the probability will become very small. It basically means that the Shannon code is pretty good. Okay, so let's prove it. Again, the proof of this, it just involves some computation here, right? So remember here, because we consider probability inside, right? So this will be a random variable. Okay, so this xn is notation of the random variable. So if it's a realization, we use x lower bar. Okay, so that's a random variable. So we just need to compute this probability. Okay, and you compute the upper bound of it. Okay, let's see how we can compute it. So the first thing we need to do is that we need to plug in L xn exactly, right? Because Shannon code, we know what L xn is, right? So that's the ceiling of log minus px. Pxn, right? Ceiling. Okay, and this guy is bigger than or equal to this. Okay, So now we need to get rid of this ceiling, right? So this is something that we always do, right? And we need to have an upper bound, okay? Then, it's either we just take it inside or we take it inside plus 1, right? But because it's upper bound, what should I do? So we should just do this, or we need to add a 1 there. Exactly, because the probability, if I add 1, so this guy becomes bigger, then the probability of this guy bigger than that will be higher, right? Okay, very good. Okay, and then next step is we just do some manipulation here. So now we have this guy bigger than L prime plus C minus 1. Okay, and then we just take the log on both sides, right? So now we have a negative sign here, right? Then we just need to reverse the sign, and then we not take the log, take the exponential, right? So this would becomes the probability that the probability xn less than or equal to 2 power of minus this plus minus c. You take the negative sign here, plus 1. Right, so yeah, if you see here, we just multiply negative sign on both sides and then take 2 to the power of this guy and to get this, right? Okay, very good. Okay, then what should I do, right? So here, kind of, how can we continue our manipulation, right? So now we need to think one thing here, right? So what does this mean? The probability of P is less than this. What's the meaning of it? Right, so what is inside is kind of like an event, right? But the event is characterized by the value of the probability, right? So it basically means that we need to, count all the probability when this guy is less than or equal to this guy. Does that make sense? Okay, so this equals the probability that this guy is less than or equal to this guy. Kind of saying nothing, right? So yeah, let me write it, then it will become more clear, right? So we need to sum for all the event, right? The probability of the event such that we have an x, the vector realization, such that px is less than or equal to this guy, bar plus minus c plus 1, right? So we need to sum, so this is all the event, right? And then we need to add the probability of all this event together, okay? And they are disjoint. Does that make sense? Right, so this is the meaning of this probability, right? We need to understand two things, right? One thing is here, okay, so this characterizes the event, right? Second thing is that the events are disjoint because x are different. Is that clear? Right, this is a key step, right? If you can interpret this term as this, then we're almost done. Is that clear? Okay, so great. And then next thing is that, so if we have that, right, so what is the magic of it? So we know if we do this sum, the probability here will always be less than this term, less than or equal to, right? And remember that what we do want is upper bound, okay? Good. And this will give you upper bound, right? So basically, what we need to do here is this less than this guy, and then here we replace px by its upper bound. Okay, very good. Okay, then we do a little bit one more step here. So we have a constant here, 2 power minus c plus 1. We take that out, right? Because that is not a function of x, right? We take that out. So we have 1 over 2 power c minus 1 in front. And then we have our big summation. Two power minus this guy. Okay, very good. Okay, then what is that? Or can you give me an upper bound of it? Yes.
That's Kraft inequality?
Exactly. Very good. Kraft, right?
So it's less than 1?
Exactly. Very good. Right, because Kraft, and then it has to be less than 1. Because we use Shannon coding, right, and we know that, it's uniquely decodable, then they must satisfy the Kraft inequality, and then this guy will be less than 1, right? Okay, and then we say, okay, this guy will be less than, replace 1 by this guy, and then we finish our proof. Okay, it's pretty tricky proof. All right. Any questions? Okay, right. If anything does not, go through, just review it offline. Okay, I think the proof is not very hard, but it's very tricky. Okay, and then so let's see the universal compression. Of binary sequence. Okay, so now we assume that we do not know the PMF of any sequences, right? Then, so if we do not know the PMF, so normally we use the word arbitrary, okay? So we consider an arbitrary sequence, so denoted by X. So that's 0 and 1 only because we consider the binary case. Okay, it only has 0 and 1, and we do not know PMF. No PMF. Okay. Or, yeah, no basically means that we don't know that, okay? So now what we do is that we consider a offline coding, so which means that we can observe the entire sequence, and then we're trying to compress it. Okay? So basically, we consider a universal offline algorithm. Yeah, universal here basically means that we do not know the PMF, right? So basically work for any PMF, okay? So now let's see how we can do it. Or do you have any idea on how should we do it? Yes?
So we get to observe everything we're trying to encode before we encode it, right?
We're trying to encode before we encode. What do you mean?
So we get to see all the data we're trying to transmit.
Exactly.
And we encode it and transmit it.
Exactly. Yes.
So couldn't we just construct a PMF based off the occurrences of things in the stuff we're trying to transmit?
Yeah, that's one idea. Yeah, I think that idea should work. Yeah. So yeah, but what we're doing is much more stupid than what you are saying. Yes, very so basically, what you just said is that okay, so we don't know the PMF, but we can estimate it, right? But here we say okay, we don't estimate it. We will do more, brute force stuff, right? We absolutely assume we have no knowledge about PMF. Yes, more stupid than what you just said, for sure. Okay, yeah, let me explain what we're going to do here. It's really a very simple algorithm, okay? But surprisingly, we do not lose, we lose a little bit, but we don't lose like really big, even if we do not know the PMF actually. Yeah, so we have a two-step here. So step 1 is that we count the number of ones in the sequence, okay? So we count the number of ones, okay? And this number is given by k, right? So that's equal summation of the entire sequence, okay? And then we use a small x here to indicate, it's an indicator to say it is a 1, right? So this means that if x is 1, then if the symbol is 1, okay? And then this equation will just give you the number of ones, right? And so the second step is also very easy. So now we know how many ones we have there, right? And then we just will give an index for each case. Okay, and then we just binary encode the index, and that's it. Okay, let's see what we mean here. Okay, so what we do here is that we give an index to the sequence with k ones. Okay, so think that way. So now let's say the total length is n, and the number of ones is k, right? So how many possibilities do we have? Right, in total we have n locations, kind of, and k of them is 1, right? How many cases do we have? It's a combinatorial problem, right? It's a counting problem, right? It's like, okay, now in total we have n positions. So we know k of them is 1, the rest is 0, right? And how many possibilities? N choose k, right? Very good, right? So in total, we have n choose k. So that's the total number of possibilities, right? Or, so do you know what this means? Right, just pick k out of n. How many ways you can pick it, right? Okay, great. And then, so now we need to represent it, right? So basically we use binary digit to represent it. So basically how many digits or binary numbers do we need? Right, is log 2, right? So this is the total number of cases, and then we just take log 2 of it, and then this means the total number of bits do we need to represent it, right? If it's 4, then we need 2 bits, right? If it's 8, we need 3 bits, and so on, right? Okay, then we just need to take a ceiling of it. Okay, in this case, we just need this number of bits to represent it, okay? And we also need some bits to represent the first case, right? So basically the idea is that, okay, so the first group of bits I receive, it tell me how many number of ones do we have. And then you tell me the index, right? That's how we code it, right? Okay, now let's see in the first case. So how many bits do we need to characterize the number of ones? Right, so basically we need to see how many cases do we have for the 1, right? We can have 0, 1, and we can have all ones, right? And then how many cases do we have? From 0 to n, right? Is that clear what I'm asking? So basically, we have n ones in total, right? And then we need to know how many cases do we have there, right? We can have 0 ones, 1 1, 2 ones, 3 ones, until n ones, right? So therefore, in total, we can have n plus 1 cases, right? Then we just need to code it. Log 2 based on that, and then take a ceiling, right? So we need this number of bits to code it, right? Is the idea clear? So basically now, in the first case, we need this number of bits, and then we need, in the first step, we need this number of bits. In the second step, we need this number of bits, and in total, we just need this plus that number of bits. That's our code length. Okay, it's the same for all the code word. Does that make sense? Okay. Okay, then the code length for any code word is given by this log n plus 1 plus ceiling of log n choose k. Okay, for all the log is based on 2, right? Just ignore that. Okay, so now we want to know the performance of it, right? So would that be comparable to if we know the PMF? Okay, so let's see how we can compute it. We just need the upper bound of it, right? So we get rid of the ceiling here to get upper bound as usual. Plus 2. Okay. Okay, and then let's see. So the first one is pretty okay, right? Log is not difficult. But what is the second one, right? How can we compute that explicitly? Right, it's kind of hard. Yeah, who knows how to do this? Yeah, good. How to do this?
N factorial
Very good.
Times n minus.
Exactly. Yeah, that's the formula, right? But it's not enough, right? Factorial is also a hard thing, right? Then what do we do? So we need to approximate or find the upper bound for the factorial, right? We don't want factorial there, right? So we use Stirling formula to do that, okay? So basically, I will ignore that. So I'll tell you what is the result. So basically, we can prove that, just use the Stirling formula for factorial. It's pretty straightforward. So we can upper bound this guy by the following, right? So it's a log of square root of n over pi k n minus k and 2 power n times h2 k over n, and that's it. And for this guy, so that should look familiar. So this is the binary entropy function. Okay, or this H2P basically equals to P log P minus 1 minus P log 1 minus P, right? So the binary entropy function, where in this case, obviously we assume that P equals to K over N. Okay, so this is a binary entropy function. So this is the upper bound. We'll just use the Stirling formula to prove it. So add 2 in the end. Okay, and if we know that, then we can do some manipulation here, right? So basically what we can do here is that, okay, so we keep the first term, right? And then, so we can keep this term, so, or we separate this term and this term, right? We have 2 to the power of this guy, right? So we can take this thing out, okay? So basically, for the second term, we keep this guy, okay? And then we take this guy out, or log 2 power this, right? We just have n h2 k over n, okay? Add 2. Okay, so we're almost there. So now we can see that. So we take this n h2 k over n in front, right? And then, so here what we do is that we take this log square root of n out, okay, to have a half log n, okay? The reason we're doing this is that we want to combine this 1 plus n and the denominator here, okay? You'll see in a minute that why we want to do this. So we have 1 plus n divided by nk, n minus k, and then plus 2. Okay, very good. So now we need to make a assumption here. So let's assume that n and k is comparable, or meaning, you know, n over k is a constant. So let's assume if n equals to alpha times k. Okay, so in that case, so where alpha is a constant, okay, in that case, we can see that, so this guy, you can see we have an n upstairs, and then we have n times k downstairs, right? So in that case, if we let, let's say if like k goes to infinity, okay, yeah, here's pi, not n, so it's just typo. The pi here. Okay, so you can see we have a k. Yeah, I mean, it's really unclear here. Let me rewrite it. So square root of pi k times n minus k, right? And you can see that we have order n upstairs and the k times n. Both of them are order n, so it's n squared. And if you take square root, it's n again, right? When k or n goes to infinity, so this guy will convert to a constant. Right, so basically what we have in the end is as follows. So basically the first term, yeah, this term is nothing. K over n is basically the probability distribution, right? So it's our entropy, right? Then the first term is NHX, right? So this is the term we want, right? And this is the best we can achieve if we know the PMF, right? Okay, and then we add the second term, which is half log n, and then we add some constant in the end. Okay, so if we divide by n on both sides, right, so this constant will disappear when n becomes large, right? The only thing that does not disappear is basically this guy, okay? And this is exactly what we lose if we do not know the PMF, right? So this is the cost of ignoring PMF of X. Okay, so yeah, basically if we know nothing about PMF, so this is how much we lose. Does that make sense? Asymptotically. Okay, so very good. Any questions? Okay, so let's continue. Okay, so basically this is kind of redundancy that we obtain, right? So we do not compress our source into the extreme, right? We have this much of redundancy. Okay, so this can also be understood as our redundancy. Right? If there's no redundancy, then we're gonna get our entropy, right? But we don't get it, so this is a redundancy, okay? But this is obtained from a offline algorithm, as we just mentioned, right? Which is not desirable, okay? So basically, it means that if we want to code a book, then we need to know the whole book beforehand, and then we do this, okay? So that's not good, right? So what we do want is a online algorithm. It basically means that, as we observe as we observe the symbol one by one, it's better to encode it online and send it. So that is what we want, right? So basically, so what we want is a universal online algorithm instead of a offline algorithm. Okay, so basically it means that we don't know the number of ones beforehand, right? But can we still do something similar? Okay, the answer is yes. So this comes to our very last topic, I guess. Yeah, this is our last topic for chapter 5, so it's Lampel-Ziv coding. Or we call that Lampel-Ziv78 universal compression. So this was introduced in 78. Okay, so there's a version in 77 and there's another version in 78, right? So we just covered the version in the 78. Okay, so yeah, let's see. Okay, so we have 3 minutes. So yeah, let's see how it works. Okay, so now let's consider a sequence X. Okay, so now we do not assume they are binary. Not necessarily binary. Okay, they're not necessarily binary. So basically, yeah, let's see an example of how we can do it, right? The procedure is very, very simple. So the first step is that we need to do a parsing. It's called LZ78 parsing. Okay, so what we do is that at each step in the parsing, so we parse the shortest block not yet appeared before, right? Let's see what do we mean by this exactly, right? So basically, let's see an example here. Let's see our sequences using some letters for the sequence of our A, B, B, A, B, B, A, B, 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 A, A, B, A, and so on, right? So the parsing is like this, okay? So basically, we just parse, the sequence that we see first, right? So now the first one is A, right? There's no A appear before, so we do a parsing here, right? And then the first parsing is, the first is A, okay? And next one is B, right? So do we see B before? No. Second one, we do a parsing here, okay? And then we have a B. So this is the second symbol in the coding, right? How about the third one? Third one is B. We see B before, right? So we do not parse here. But how about BA? We don't see that before. So the third one is BA. Okay, and the next one is B. We see that. How about BB? We do not see it, right? We do a parsing here, BB. So those are basically our coding symbols. Okay, so we're going to use some index to represent those. And how about next one, AB? Do we have it? No, right? Okay, do a parsing here. So we have AB. And next one is we have B and we have BB. And do we have BBA? No. Do a parsing here, BBA. And next one, so we've seen AB before, right? AB is here. So, but ABA we didn't see that. So we have a parsing here, ABA, and so on, right? So this is a parsing. Okay, this is step one. Okay, and after the parsing, we're going to do the LZ78 encoding. So, yeah, what it does, let's finish it. It's very quick. So we are going to basically assign to each parsed block the index of the prefix previously appeared. Okay, and here important thing, we need to add additional new symbol. Additional new symbol. Okay, so what it does is as follows. So basically, yeah, let's say, let's use the previous example here to write here, so it will be easier. Okay, use another color here. So basically, what we do here is that we need to assign an index to each of them. Okay, so basically, we use a 0 as a starting point, and we assign the first one as 1, 2, 3, 4, 5, 6, 7, and so on. Right, so what we do here is that, so the code word for the first one is the index before, right, which is 0. And then we're going to add this guy here, A. Okay, and for the second one, so it's the index not appeared before, right? The second one is still 0, and then B. Okay, so how about the third one? BA is not appear, right? Again, so we have a 0 for and BA. Oh, sorry, no, it's not like that. So B is appeared, right? So here we have a B here is appeared, which is 2, right? So basically what we're going to have is 2 and A. Okay, and for the next one, okay, we have BB. So B appeared before, right? So it's 2 and then B. And for the next one is AB, and A appeared before. A is what? A is here, right? So we have 1, B. Okay, and how about BBA? So BB appeared here, right? The index for BB is 4, so I have 4A, right? How about next one, ABA? So, and AB appeared here, it's 5, so here's 5A, and so on, right? And those are our code word. Is that clear? And you can see the benefit, right? So every time we just, we just code whatever before by using a one index, and then, add a new symbol here, right? As it goes by, it will save more and more. Okay. And so this is basically LZ78 coding, and so those are the code word we send, right? So if you want to send binary, just encode the first one using a binary sequence, and the second one is a binary sequence as well, right? Okay, and we have a theorem here. So we do now prove this theorem. So you can see, so you can check either in the book or ChatGPT how we prove that. So the proof of it is not very difficult as well. Or you can think about yourself, right? Asymptotic optimality of LZ78 code, right? So basically, the theorem says that the limit n goes to infinity, and if we take a soup of this guy, the length of the code, okay, and this will be less than the entropy rate. Here is the calligraphic x. So this is the entropy rate. with probability 1. Okay, asymptotically when n goes to infinity, you can see this code is optimal. Okay, and you can think how we can prove that, right? So the idea of proving that is not very difficult. Okay, and now we finished talking about our chapter 5, and from next class, we're going to talk about chapter 7. Okay, we're almost done with everything before Christmas. Oh, sorry, before midterm. Yeah, I'm thinking too much about holidays probably. Yeah, so there's a one very small part that might be included in the midterm from chapter 7. Okay. Okay, great. Yeah, thank you.